Hi, welcome to the second part of my Morse Code Keyer video. And this is our little device. This is the Morse Code Keyer. If you haven't watched the first part, you can do that by clicking on the link somewhere here, or you can find the same link in the description of this video down below. We use this little device to send Morse code signals, and we connected it to Commodore 64 through user port. And now it's time to write a little bit of assembly code so that we can capture those signals and determine the difference between dots and dashes. So yeah, let's begin. And here we are, finally ready to write a little bit of assembly code. Now, if you remember from the last time, I modified this little circuit that besides this PB0 pin that we are monitoring, that's connected to our Morse code keyer, we inverted that signal and we push it through the flag 2 pin. So basically we are pulling the flag 2 pin down whenever this PB0 signal goes high and vice versa. Now the reason why we did this is simply that we can use external interrupt routine on CIA chip number 2, and that, to be precise, that's NMI interrupt we're going to write. And this first step that we're going to do now is just to test whether or not our circuit is working, and we will write a simple external NMI interrupt routine. We will try to change color border or screen border or whatever, just to see whenever we press a key on our keyer that we have interrupt active on Commodore 64. So yeah, let's do that. I do plan to develop most of the code on Commodore 64 using MIKRO Assembler Cartridge, simply because, well, when dealing with I/O lines, it's much easier to have everything hooked up, and that I can test the code and debug the code and everything else. So yeah. So okay. So firstly, we have to tell where our program is going to be stored, or where our program is going to start in memory of Commodore 64. So we do this by defining hex 1000. Our little program is going to start at memory address 1000 hex. And now I'm going to define two variables, or to be precise, two memory addresses that are related to CIA2 chip, and those memory addresses are interrupt vector low equals to 0318 and interrupt vector high equals 0319. So these memory addresses should contain a pointer vector to our interrupt routine. So pointer vector is, well, that's just a value of a memory address where the interrupt routine is going to be stored in the memory of Commodore 64. So we have to tell, once the interrupt happens, the kernel will jump into these addresses and try to read the values from these addresses, and these values should be 16-bit number, which is the memory location of our interrupt routine. So I hope that I explained that in some understandable way. Yeah, so for that reason we have two memory positions. First one is for the low byte, and the other one is for the high byte, because except for the 0-page memory, every other memory address on Commodore 64 is 16-bit number. So yeah, Now we have to configure our NMI interrupt, our external NMI interrupt. But before we do that, it's a very good practice to stop all the interrupts on Commodore 64, just to play safe. And we will do that with the command SAI. So now all the interrupts are stopped, and now we are going to make some changes. First, we're going to fill these two addresses with a pointer to our interrupt routine, and our interrupt routine hasn't been written yet, but we will have to assume, well, you will see we will have to assume that it's kind of is. So we are going to use the label of our interrupt routine for the compiler, so that compiler can calculate later exactly which memory position is that. So yeah, you will see. So firstly, we are going to load into accumulator low byte of our interrupt routine, and let's give her a name, or the label to be precise. So it's going to be called interrupt routine, something like that. Okay, that's fine. And now we are going to store this number into low byte, IV low. So we are going to store this number low byte into this variable, or to be precise, we are storing it in memory address 0318. And we have to do the same thing with the high byte. So we have to load high byte of our interrupt routine, and of course store that value as well. So we are storing high byte of our interrupt routine into memory address 0319. Okay, so far so good. So the next thing that we need to do, we have to activate our NMI interrupt, right? And we have to define the source for our NMI interrupt. So in this case, it's a external interrupt on flag 2 line. So to do that, we will have to load accumulator with a number again, and this time I will write this number in binary form, just to it's going to be much easier for me to explain how this register works. And before I write the number, let me specify the register. So we are going to store the value into register DDOD. Now this register is the CIA2 interrupt control and status register. So that means that it does behave a little bit different than we are used to. So let me write here 8 zeros, so 1, 2, 3, 4, 5, 6, 7, 8. So the first 5 bits of this number, or from bit 0 up to bit 4, behaves like a mask. So that means that if we specify this bit number 7 as 1, we are setting up the bits, or we are setting up the mask. If we define this bit 7 as 0, then we are clearing the mask, so we are clearing the bits. So in our case now we need to set the bit, so this bit 7 needs to be 1, and our NMI external interrupt on flag 2 pin is defined at bit 5. So here we have to define this as 1, and this is the value that we are going to store in a memory address DD03. Every other value here, for this bit 0, bit 1, 2, and 3, they are left as the zeros, so that means they are not going to be changed. In case when we want to stop this or disable this interrupt, instead of 1 at the beginning of bit 7, we need to specify 0, but we have to leave this 1 here, and this value now will affect in such a way that it will disable this interrupt. So, but in our case now we have to write, so we have to set our interrupt here. So this will now activate our external interrupt on flag 2 pin. And that's all that we need to do for the configuration or for the setup. Now that we are done, we can re-enable all the interrupts on Commodore 64. So we will do that with the command CLI. And the next thing that we are going to do is we are going to exit our program with the command RTS. Now, why we are doing this? Well, we can easily exit our program because that's the whole point of these interrupts, so that we can exit our code, exit our program, but the interrupts are going to be still active and live and waiting for the trigger to happen. So yeah. And there is one more thing that we need to do, and that is write our interrupt routine. We haven't done that yet. So let me do that. So of course we have to use the label that we specified here. So label is going to be interrupt that's fine. And for the moment we are not going to do anything special in our interrupt routine. We are only interested to see whether or not the interrupt is going to trigger. That's it. So for that reason we are going to just increment the border color D0 to 0. So that's the memory location to define or to specify the border color, and every time that our interrupt is triggered we are going to increment the border color by 1. That's basically it. Now, before we exit our interrupt routine, there is one important thing that we need to do, and we need to clear the flag. We need to clear the interrupt flag so that we can re-enable the interrupt handler. So that means once the interrupt is triggered, in this case NMI interrupt, the NMI flag is going to be set. As long as the NMI flag is set, there will be no other or new interrupt triggered on the system. So before we exit our interrupt routine, we have to re-enable or clear that flag so that we can enable the next interrupt to trigger. So to do that, we need to use this bit command on memory register DD0D, and of course this DDOD is interrupt control and status register for the CIA2 chip, as we had that same thing before here. So yeah, makes sense. And now we can exit our interrupt routine with command RTI. RTI. And we are done. Now let me list this code and check every line. Do we have everything right? And I hope that we do. Yeah, seems good. Okay, let's try to assemble it. And we have all 3 passes. Good. And we have our start address at hex 1000 as we specified this in our program. So to call our little code, we need to call the sys command, and hex 1000 is in decimal 4096, so we have to call 4096, and I fucked something up. What the hell happened? Start address is 1000. D0 increment. Did I fuck up those addresses? No. Maybe I didn't load. I have error. Store. Oh my god. I did have an error in my code and I didn't get it. Oh, bloody hell. Okay, one more time. Okay, so I hope this will work now. So, okay. Yeah, now we're talking. And here we go. We have our NMI external interrupt active and working as expected. So that's really nice. So these are dots and these are dashes in manual mode. So if we switch to auto mode and set some speed, so these are dots and these are dashes. Now let's speed up a little bit more. So these are dashes, these are dots. They're quite fast. I mean really fast. And we can do even faster. Now these are dashes and these are dots. That's fast. Nice. Okay, so yeah. Let me do something else. Let's switch to white and list the program one more time. Okay, so we are ready to start develop this code a bit further. And now, once we are able to detect the high signal from our Morse code keyer with the external interrupt, once we enter our interrupt routine, we can now start to monitor PB0 pin and try to measure how long the signal is going to be high and try to determine whether it's dot or dash or dash. Yeah, so yeah, let's do that. Okay, so this is our code now. It's a little bit more than in previous example with just NMI interrupt. And I decided to use text editor simply because it's easier to explain and jump all around the code in this way. But we will certainly take a look at this code on Commodore 64 so as well. Again, we are starting at memory address hex 1000. That's where our program is going to be stored, and we need to set up PB1, that's pin 0, at port B on user port on Commodore 64 as input. That's our main pin that will receive our signals. And we're doing the same thing like we did in the basic example. This port B is under control of CIA number 2. So in memory address DD03, that's the register for the port B direction, and we masking the last, or masking the entire memory address, and what we want is the bit 0 to be 0. That's basically it. So we are loading that value, we are masking it or ANDed it with 254, and then we are storing that back to that memory location. And then we define a couple of variables here that we are going to use. So you already saw these two, which are memory addresses for the where we're going to store vector to our interrupt function or interrupt routine. And then we have two new variables. It's first one, dado. It's where I'm going to store the character that we receive, or the signal, whether it's dot or dash. Simple as that. And this delay variable, we will use it as a counter. If we don't receive any signal for a certain amount of time, we are going to jump into the next line. That's basically it, and we are going to use that variable for that. Of course, it's not enough to use just 1 byte, so we will use delay +1. So we are also going to use memory address FD as well here. Okay, So again, the same procedure. We need to stop all the interrupts on the Commodore 64. You already saw this, so we are storing our vector or address where our interrupt routine is going to be stored, so the low byte and the high byte, and we are activating NMI interrupt on the external interrupt on the flag 2 pin on user port on Commodore 64, and then we are reactivating the interrupts or activating all the interrupts again on Commodore 64. Then the next thing that happens, this here is a little setup before we enter our main main program loop. This time we will not exit the program completely like we did in this in that NMI example. This time we will stay in the program. We are going to loop constantly, and we are checking a couple of things. So we are resetting our delay counter, so it's a 16-bit counter. We are resetting it all to 0, but we are going to change that, and I will explain why in a second. Then we are entering a main loop of the program, and that goes from this M loop up to here. That's our main loop, and all we do here is simply increment our counter, our 16-bit counter, and once we reach 8000 hex in our 16-bit with our 16-bit counter, well, in that case we are going to execute this part of the code, which will just jump into the next line, move the cursor into the next line and into the column number 0, so the first column. That's it. So, and I will explain why we are doing this. And once we reach this 8000 hex, the next iteration of this loop will check whether or not did we reach this 8000 hex. If we did, the counter will not progress further. It will just stay at 8000 hex. That's it. So it will not constantly produce new lines. Okay, so the next thing, if after that we are checking one of the registers on CIA1 chip, and that's on port B, well, we are checking whether or not the user hit space key on the keyboard. In case it did, we are ending our program and we are exiting here. In case it didn't, we stay in constant loop. That's basically it. We are still missing here something, so I will add here, let's say 292, 293. Yeah, we will need 2 lines here. Also, the way how I set it up, this will, once it started, the program will, after a certain amount of time, short amount of time, it will produce the new line, because our counter is going to start counting and we will reach 8000, and the new line will be executed here. To prevent that, instead of setting our counter at 0 at the beginning, we will do something different, and we are storing 000 in a low byte of our counter, but we are going to store hex 80 in a high byte. So that means that we are at the beginning, our counter will have value of 8000 hex, and that means it will not start counting until something happens, and I will show you what will happen. And it will happen in the interrupt routine. So in the interrupt routine, once we receive the signal, we will start our counter. So we will reset it to 0. It will begin to count, and it will try to go all the way up to 8000 hex. And every time that we receive a signal, new signal, That means every time that our interrupt routine is activated, or we will reset this timer. So that means that this timer will be constantly resetted as long as we receive new signals. Once we stop receiving those new signals, our counter will continue to count. It will eventually reach 8000 hex and it will produce new lines. So that's basically it. Maybe I could do this in some different way, but this makes sense to me. Okay, so we solve first problem with our counter here. The second problem, I will go back to this. Okay, I can do this now. Okay, so once the user hit the space key and we detect that we have space key pressed on the keyboard, we want to exit the program. Now what will happen with our interrupt? Well, it will keep going. So nothing will stop him if we just exit our application, our program, without anything else. So we need to deal with that as well. We need to stop our interrupt. The way we stop the interrupt, and I will copy these two lines here. So we need to stop all the interrupts, and I will enable all the interrupts again, and so here will be 21293. Oh, okay. We are up to the numbers. Okay. This looks ugly, but yeah. And this is where we set this pin to high to enable our NMI interrupt, and we store that in the memory address DD0D. The way how we clear that bit, the way how we remove that interrupt is, instead of and this is important bit here, that's bit 7, which defines whether are we setting the bits or we are clearing the bits. So if I set 0 here, everything that is defined as 1 or set to 1, it will be cleared. Everything else that is 0, so all these zeros, well, those zeros will remain as they are. They will not affect in any way those configurations. So yeah, that's how we stop the NMI interrupt. So stop NMI interrupt. Okay, so that's something that we didn't have in our code so far. And now we have reached our interrupt routine finally. So yeah, it's a little bit more code than before, and again I will explain why. So firstly, we are doing something here that I haven't done in that NMI example, and maybe I should. It's a good practice to do, especially when we are dealing with interrupts, because interrupts will stop the main program and jump to interrupt routine, execute some other part of the code, and then return and continue executing the main program, whatever that was. So it's a really good practice to store all the values from the registers to the stack, and then before we exit our routine, return those values from the stack back to the registers, so we are playing safe. And that's what we are doing here. We are loading value from our accumulator to the stack. Then we are transferring value from the X register to the accumulator, and then again pushing the value from the accumulator to the stack, and we are doing the same thing for the Y register. In the end, when our interrupt is done, interrupt routine, before we exit, we are going to do the same thing here, except in the reverse order, and that's basically it. Okay, so again, in our interrupt routine, we again have some counters, so I will explain those as well. Again, it's 16-bit counter, But firstly, what we are doing here, we are resetting our main counter from the main program. We are setting it up to 0. And what I'm missing here, oh bloody hell, let's say 47, delay +1 also needs to be set to 0. Oh my god. Okay. So we are resetting our counter now to 0. That's very important. Now the next thing that we are doing in the variable dado, this variable, I named it after dash and dot, dado, whatever. So immediately once we receive the high signal on our flag 2 pin, at least we know, at least it's a dot. So for that reason, I use Petsky character in hex 71, which is like dot, small dot. That's it. So that's something that we already know. We at least receiving a dot. And then what we are doing next, we will set up counter again, 16-bit counter. In this case, we are going to use X and Y registers to count until our signal goes low. But this time we cannot read the value of the flag 2 pin. We cannot control it. Now we are switching to pin PB0, which is our main pin, and that's the pin that we are going to keep reading and waiting until it goes low. So that's basically it. So this is our loop. This is our loop. So in this loop we are incrementing X and Y registers, and once we reach this certain value, so in this case it's 1400 hex, everything up to 1400 hex it should represent dot. If we go beyond that, then we are assuming that we receive a dash, so the longer signal. And this value here on line 395 is something that you need to tune up a little bit, because it really depends on the timing, because if I crank up the speed all the way to the maximum, these values should be adjusted accordingly, because my code is not will not auto detect the difference between the dashes and dots, so you have to tune that in the code itself. Once our counter reach that 1400 hex and it's going beyond that, then we are assuming that our character that signal that we are receiving is the dash, and then I change the value of this variable dado to hex value 63, which is just Petsky character dash. That's middle line. That's basically it. So yeah, and the next thing that we are doing, and we are, because we are in the constant loop, we are always need to check in every iteration, is our pin PB0 still high or it's went to low. So that's the register DD01, and we are loading that into accumulator. We are masking everything except the last bit 0. So after we end our accumulator with 1, all we can have after that is either 0, or if pin went too low, it will be 0. If it's still high, it will be 1. That's basically it. And now we are checking or comparing that value with 0. So we are interested in signal going low. If it's not 0, so this is this line here, if it's not 0, that means it's 1, it's still high. We continue cycling through our loop. Well, in case it's 1, we will exit here. And what we are doing here, we're simply loading character or variable with value of PETSCII character to the accumulator and using one of the kernel routines to print out that character on the screen. That's basically it. The signal went low, we need to exit our interrupt routine, we are done. We still need to do a couple of things. So firstly, we will again reset our main counter. We acknowledge that interrupt has happened, and that means that the next interrupt can happen. So that's basically it. And before we exit our interrupt routine, we are doing this, like I mentioned before. We are pulling the values from the stack and returning them back in the reverse order. So first we will return the Y register, then the X register, and then in the end we are going to pull the value for the A accumulator, right? So, and then we are exiting our interrupt routine and we are exiting clean. So that's good. And this is the whole code so far. So what we will expect on the screen is just when, as we send the signals with our keyer, we'll expect to see detection whether it's dot or dash, and once we stop sending the signals after a certain amount of time, the cursor should switch to the new line. That's basically it. So that's the whole code. So let me show you that on Commodore 64, and then we can continue developing this code a bit further, because yeah, there is this is the Morse code. We need to know which letter has been sent or which character. So yeah, we still need to do that. Okay, but firstly let's check what do we have so far. And we are back with actual Commodore 64 and our Morse code keyer. So yeah, let's power up the keyer. Let's test it. Yeah, still works. So let's load our little piece of code. And see how it behaves. So I'll slow this down. So yeah, a little bit more than before, but nothing terrible actually. So let's assemble this. And we're good to go. Oh, we already have that. Okay, as you can see right here, we have a little dot, and this should give us dots, yes, and this should give us dashes. As you can see, when I press, when I stop sending signals, after a certain amount of time, it will just jump into the next line. So yeah, we have dashes and dots. And let's see if I speed up a little bit. And we are in the oh, now it's auto mode. Oh. Okay. No, this is manual, sorry. This is now auto mode. Yeah. Yeah. Nice. Sounds great. It does sound like some important messages coming. And if I press both of the oh wow. Okay, so yeah, here you go. So yeah, it's working, and it's working nicely. And now when we exit our program, our interrupt shouldn't be live anymore. So yeah, like you see, nothing yet. Nothing on the screen anymore. If we start all over again, yeah. And why do we have a dot at the beginning? Something happened at the beginning. Okay, so yeah, this is it. This exits the program. Okay, so yeah, let's now continue further and try to decode these messages into the letters. Yeah, that's the next step. And this is the end of part 2. So the next time we will write a little bit more assembly code. We need to determine, or better say decode, those signals back to the letters, and we will take a look at Morse code charts, and I will show you how I made my lookup table that I use in assembly code, or that we will use in assembly code to decode those messages back to the letters. So yeah, until the next part, goodbye.